So we've been talking about obviously kinetics here in the last chapter, and as we've spoken about, it really does deal with the idea of how fast or slow a reaction takes place. Um, the other day there, we talked about what's sometimes referred to as the rate expression, and the rate expression in general, when you have a reaction, say A plus B goes to say C. We basically could write it's really sort of a derivative, but it is the rate is equal to minus 1 over A, change in concentration of A over the change in time. And that would equal minus 1 over B, the change in the concentration of B over the change in time. And that would equal 1 over C, change in concentration of C over the change in time. Now, a couple of things that we talked about this sort of important in terms of sort of signs and what's going on here. First off, as we talked about, these reactions, are pretty much assumed to be heading from reactants to products. So what we could probably safely assume is as time goes on, our reactants should be decreasing with time and our products concentration should be increasing with time. And that's what these sort of negatives are here for in these expressions. These negatives are to indicate a decrease in concentration over time of our reactants. And that's why, again, we see it here with our reactants, but not with our products over here on this side. Again, because the products are basically increasing with time. So we do get a positive. When it's all said and done, this is kind of what is referred to usually as sort of the average rate of the reaction, as we talked about. That's so again, sort of, kind of the overall rate at which things are changing from beginning to end in the reaction. The 1 over the coefficient part, where we take 1 over these coefficients in the balanced equation, that again takes care of the sort of stoichiometry part of it. So that takes care of all that stoichiometry part of it. So you have the right mole-to-mole relationship. So as we saw, I think yesterday, if you kind of do the 1 over the coefficient, it sort of takes care of the stoichiometry part with the sort of kinetics part of the calculation, and you're all good to go. You could, as I think we did on the last example, again, you could kind of just do it as a basic kind of stoichiometry problem, a mole-to-mole problem, and then incorporate things like volume to get molarity and time to get kind of the molarity over a unit of time and kind of the kinetics part of it at the end. Now, these guys here, when we do calculate the average rate for the reaction, that usually is a positive number, as we've been talking about. And again, that's why the importance of those negative signs, because as we've seen, if A is a reactant, where it starts at, say, 5 or 6 molar, when it's done, maybe it's down to 4 molar. To get the change in the concentration of A, that is basically the final concentration minus the initial concentration, which in this case would be like 4 minus 6, gives us 2 molar, which would be negative. And again, that negative indicates that it's decreasing with time, along with the negative on the outside will turn our rate into a positive number. That's not needed on the product side, because if we think about the products, usually it starts at 0 and ends somewhere, say 2 molar, for example. So when we do the change in the concentration, for example, of C, it goes from final, which is 2, minus 0, which is initial, gives us a positive 2 molar change. And again, with nothing there, that keeps it a positive overall rate. The nice thing about sort of the rate expression is it does allow you to sort of understand or figure out what is going on with everybody in the reaction, both reactants and products. And we really just need kind of one piece of information, because as we did in a couple of those sort of problems, you can separate these out individually and go, hey, the rate is equal to minus 1 over A, change in concentration of A over the change in time. You could also do the rate is equal to minus 1 over B, change the concentration of B over the change in time. And what sort of ties these together is this number here, that average rate, that is the same number. So again, we can kind of individually use these guys like we did in those couple of examples, get the rate, use that rate then to find, how things are changing. So as we talked about last time with it, again, usually positive number here. If you're asked to solve for something like how the concentration of A is changing with time, since that is a reactant, that will be a negative number when you're all said and done. And again, if you're doing something like C's with time, that will be a positive number. So individually speaking, if you're interested in how each of the reactants or products are changing, your reactants will end up with a negative sort of change, and your products will end up with a positive change, and the average rate will be positive. Any questions on what we sort of talked about last time? Okay, then we're going to talk about actual rate laws here. The rate law is a little bit different than sort of the rate expression. There's a couple different things kind of going on there. So the rate law basically expresses the rate of the reaction with the rate constant and the concentration of the reactants or products to some type of power. So if we have this reaction here, we could write this guy here, which is the rate law, or a version of the rate law here. And what we see here is the rate is equal to K. The K is our rate constant, as we talked about, sort of that constant relationship that you could get in a reaction of how fast sort of something is moving. Again, here, the guys in sort of the brackets are the concentrations. A to the X and B to the Y. So the X and the Y are what are referred to as orders. And one really important thing that's sort of different between a rate law and sort of the rate expression that we were dealing with earlier is if you look at the rate law, it is all about reactants only. So just reactants are involved in the rate law, no products. So when you see a rate law, is pretty much all reactants. Are basically what goes in there. Now, what are X and Y? X is the order in this example with respect to A. Y is the order with respect to B. And it's important to note that X and Y are not the coefficient in the balanced equation. So sometimes people think, well, it's just going to be the coefficient, and that's what the X and the Y will be, but it is not. It is always found experimentally. So rate laws and orders, they're always found experimentally, which, as we'll talk about here in just a second, basically means that, you're going to be given some experimental information. You're going to use that information to try to help you determine what these orders are. What are these orders and stuff? How do these things sort of affect, the reaction rate? You can kind of think of it as sort of the proportion of, say, A or the proportion of B that you need to sort of maintain a specific rate. And we can get the overall order of the reaction by adding X and Y together. So the overall order of a reaction can be found by adding X and Y together. Again, if you have more than two reactants, you would add X, Y, and Z together, or whatever it may be, and I'll give you the overall order. But rate laws are really determined by experimental information, and you're basically be given a table of information. You need to sort of use it to figure out the rate law. So, for example, let's just say that we calculated the order for A to be 1, and let's just say we calculated the order of Y to be 2, just for example, just making this up. So what does that mean? Let's say we just put it into our rate law. So the rate would equal then K A to the 1, which, like normal, you don't really need to put the 1 there, and B to the 2. The overall order here would then be 1 plus 2, which would be what is referred to as third order reaction. And this would be what is sometimes referred to as the completed rate law when we sort of figure those things out. Once we do that, we then could rearrange it and solve for K, and K would be the rate is equal to A times B squared. And we could actually use it to figure out the actual value of the rate constant as well. But just to illustrate sort of what these orders mean and sort of how it affects a reaction rate, let's just say, for example, that we started with, in terms of concentration, 2 molar of each of those guys. So let's say we started with 2 molar of each, A and B. So let's just say we're concentration of A is equal to 2 molar and concentration of B is equal to 2 molar. If we put it into my made up rate law there, let's just see what we get sort of for the rate, if you will. So the rate would equal K, and A would be 2 and B would be 2 squared. And we're just going to kind of ignore K because it's a constant. So whatever we multiply it by will be the same number. And if we do that, the rate would then equal, for example, 2 squared, which is 4 times 2, which is 8. So we'll just say the rate would equal 8. Now, why it's good to know the orders and sort of the relationship, let's say that you decided, all right, in my next reaction, I'm going to double the concentration of B. So I'm going to start with 4 molar B. If we put that into our rate law, our rate would equal K, again, 2. And now we're going to start with 4 squared here. Again, we're not going to worry about K because it's kind of a constant. So if we take 4 squared, which is 16 times 2, means that our rate is now 32. And what does that mean? Well, it means that we would just increase the rate of the reaction by a factor of 4, right? If you take 32 divided by 8, it's 4. We basically increase the rate of this reaction by a factor of 4 by simply doubling the concentration of our reactant B. And again, if you wanted to speed up a particular reaction by knowing the orders, you could adjust the concentrations to speed up a particular reaction. You can also speed it up, maybe not as much, if you decided, hey, you're going to double, you're going to double A instead of B. So if we did that, where A was doubled to 4 and B stayed the same, which was 2, what happens in that case? Well, the rate would equal K. A gets doubled, B stays the same. We now have 2 squared, which is 4, 4 times 2, which is 16. In that particular case, from our original thing, we were able to double the rate by doubling the reactant A. You also obviously could do the opposite if you wanted to slow down a particular reaction and not allow it to sort of occur as fast. You could lower the concentration of one of the reactants, you could lower the concentration of the other reactants, and you could sort of predict how much slower a reaction would occur. You could also use it, obviously here, we would predict it to be, in this last example, twice as fast as it was originally. Any questions on sort of what those orders mean and sort of how you could use that information to help you speed up a reaction, slow down a reaction? You may be wondering why you may want to do that. For example, if you were sitting there trying to take readings of absorbance values or something every 5 seconds or 10 seconds or even 1 second or 2 seconds, and you doubled B in this case, your reaction is going to happen 4 times as fast, which means you need to be 4 times as fast to record those informations. So you may want to slow it down to allow you opportunity to actually get enough data and information in your thing. Your question of how did we get X and Y, in this particular case, I just made up X and Y's values. We're actually going to talk about how to officially get these numbers here and right now, actually. But for this example, I just made them up. But you actually do calculate those guys experimentally is where those numbers would come from. Other questions? Okay, so the importance of sort of the rate law, again, it's all about the reactants. How they react really determines how fast or slow a reaction will take place. So when we're doing rate laws, again, only reactants involved, the X and Y are the orders. And again, all this information is pretty much found experimentally. And we're going to answer that question just here in a second, how we get all these numbers and stuff. But it really is from experiments, and from experiments where you basically are given concentrations of reactants and sort of initial rates, and that sort of helps you kind of determine each of those things. So let's talk about how we actually do go about calculating those. So let's take a look at a reaction such as this, where we got F2 goes to F2 plus ClO2 goes to FClO2. And this type of table here is a very common type of table that you're given in kinetics problems. And what you typically find in these tables are at least 3 columns or so. But main things that you find is you'll typically find a column of concentrations of each of the reactants, which we have here. And we'll usually have multiple trials that were done. So these are like kind of different experiments, different trials that were done of this reaction. And then you'll usually have a column of initial rates. And initial rates are sort of, again, just based off of the one experiment and sort of what's happening for that particular experiment. And those are the 3 pieces of information that you could really use to, as we will do here in just a second, really figure out everything about sort of this reaction in terms of the rate law. So the first thing that you could do is you really can write what I sometimes refer to as sort of the just sort of generic rate law for this reaction. So if we were going to look at this reaction, remember when we write a rate law, it's all about the reactants. So the rate would equal K times F2 to the X. Again, we don't know what the order is at this point, times ClO2 to the Y. And again, we don't know what the order is at this point. Just the reactants are involved. Remember again that those orders are not from the coefficients. Now, the first thing that you really want to do when you have a table like this is you want to sort of figure out what are the orders. So sort of the mode of attack here is to figure out the orders first. That would then allow you to figure out something like what the value of the rate constant is. Now, there's a couple different ways you could do it. You could do it by just analyzing the table. And if you understand, what's happening with the rate versus how the concentrations are changing, you could look at that. I find most people really can't do that all that well. So most people need some type of mathematical approach. So mathematical approach is you could kind of use this formula here, which is the rate 1 is equal to K times A to the X and B to the Y divided by rate 2 is equal to K times A to the X and B to the Y. So this little formula here is very useful when you're trying to determine the rate law from actual tables. Now, what does rate 1 and rate 2 mean? It means you go to this table, and it doesn't necessarily mean that you actually just grab the first entry and the second entry. That's not what it means. It means that you're basically going to go to this table and you're going to grab 2 different entries. And what you're looking for when you go to grab these different entries is it's really going to be math. So when you're dealing with math, right, you don't want a bunch of unknowns. So we usually want to keep the kind of unknown things to like 1, right? And to do that in this type of problem, what you're looking for is you want to look at the concentration of your reactants, and you want to find 2 entries where one of the reactants remains the same and the other one varies. So you want to find 2 entries in that table where if you look at it, one stays the same in terms of their concentration of reactants and the other one differs. So if we actually, in this case, look at experiments 1 and 2, we see that the concentration of F2 stays the same at 0.1, but the concentration of Cl2 varies. It goes from 0.01 to 0.04. So those are the 2 that you would maybe want to tackle. So I'm going to look at experiments 1 and 2 here. So looking at experiments 1 and 2, Now, which one should you choose? In most cases, if you look at the rate and you kind of do the one with the larger rate and put that on top, you typically will end up with kind of like a whole number, little nicer whole numbers at the end. You don't necessarily have to do that. If you do it kind of the other way, you'll end up with some decimal points and stuff like that. But kind of put the larger rate guy up on top, you'll usually end up with sort of a little bit more whole numbers and a little bit easier to visualize the final answer. So what that means is I'm actually going to take everything from experiment number 2 and just put it up on top. So 4.8 times 10 to the minus 3 is equal to K, I don't know. And A for that, which is my F2, is 0.1 to the X. And for my ClO2, it is 0.04 to the Y. So basically what I did is I took everything from entry number 2 and I basically put it into my rate law up on top equal to its rate. I'm going to do the exact same thing and put everything from entry number 1 on the bottom. And that gives me 1.2 times 10 to the minus 3 equals K, and 0.1 to the X and 0.01 to the Y. First off, any questions on sort of where I'm getting these numbers? Again, all these numbers are coming from the table and put it in there. Once you have this, we could do a little bit of math here. So if we do some division here on the left-hand side, we take 4.8 times 10 to the minus 3 and divide it by 1.2 times 10 to the minus 3. That should equal 4. Now, by keeping some things constant, it helps us make this very easy to solve. First off, we have K on top and K on the bottom. Remember that K is the rate constant. So the key to that word is constant, which means although we do not know what the number is for K, we do know that the K on top and the K on the bottom should be the same number, which means that they will cancel out. So again, although we don't know what it is, should be the same number up on top and bottoms, means they should cancel. Now where we come to our F2, where we held constant in this case, we don't know what X is on top, which is the order with respect to F2, and we don't know what it is on the bottom, but we do know that it's going to be the same number, which means that these guys will cancel out as well. Coming over here, we now have 0.04 divided by 0.01 to the Y, which means we will end up with something like 4 to the Y. Any questions on that when you divide it? Now, because we kind of put that bigger number up on top, you can see what I was talking about is when you get to this point, you'll kind of get whole numbers, makes it a little bit easier. And you can probably visualize just looking at it that in this case, Y would need to be equal to 1. 4 to the 1 power equals 4, right? And that it would be what Y equals. Now, if you get a case where it's not really perfect, pretty numbers, you can take the natural log of both sides and divide it. So you take the natural log of the 4 on the right-hand side and then divide it by the natural log of 4 on the left-hand side. And that obviously would equal 1 as well. So that's a way, if you don't get kind of nicer whole numbers, you mathematically can solve it. Again, you would take the natural log of 4, and that would bring the Y down. And then you would divide the natural log of 4 to both sides, equals 1. These guys cancel, equals Y. So again, that's mathematically how you can kind of solve it as well. Any questions on that part so far? So what that means is we have now used our experimental information to figure out what Y is. And in this case, Y is equal to 1. So now what we want to do is we want to go back to our table and we really want to figure out what X is. So in this case, the first time around, we kept the concentration of the F2 constant and we varied the concentration of the ClO2. Now we want to do the opposite. We want to go back to the table and find 2 entries where the ClO2 stays the same, which is here. And the concentration of the F2 changes, which is there as well. So that looks like experiments 1 and 3 will do that for us, where we're now keeping the ClO2 constant and varying the other one there. So experiments 1 and 3. And we're going to do the exact same thing. Upon analyzing experiments 1 and 3, I see experiment 3 has the larger rate. So I'm going to put experiment 3 up on top. So we're going to do the same thing. 2.4 times 10 to the minus 3 is equal to K times our 0.2 to the X, our 0.01 to the Y. And now I'm going to put everything from experiment 1 on the bottom, 1.2 times 10 to the minus 3. Okay. And again, I'm getting these numbers from the table. And now we're going to do pretty much the same math thing here. We're going to divide these guys out. That gives us a 2. Same logic here. Don't know what K is, but it is going to be the same number, so it cancels out. Here, 0.2 divided by 0.1 gives me 2 to the X. And again, we already know that this is going to completely cancel out. And at this point, again, you could probably visually see that X in this case, again, would equal 1. By the way, the orders won't always equal 1, but just happens to be in this case. So that tells us now that the order with respect to F2 in this reaction is also first order. That means that we can now write our completed rate law, which is the rate is equal to K times F2 to the first power times ClO2 also to the first power. And that would be our completed rate law with the orders. Again, you don't need to put the ones there like in most things in chemistry. It would also tell us that the overall order of this reaction is 1 plus 1 is second order. And that is found by taking each of the individual orders and adding them together. Any questions on that? So now we've used this experimental information to figure out the actual rate law here. We could actually use this table to figure out what is the value of the rate constant in this case. So what we would want to do is take this rate law that we now have the actual orders for each of everybody there, and we want to solve for K. So if we do that and we rearrange it, K would equal the rate divided by the concentration of F2 to the first power and ClO2 to the first power as well. So your question may be, where do we get these numbers now? And the answer is you could absolutely go back to this table and you could choose any entry you like. You could choose the information from experiment 1, you could choose the information from experiment 2, you could choose the information from experiment 3. And basically you just put those values into here. So for example, I'm going to use experiment 1. And when I do that, I'm going to use all the information from experiment 1 here. And we would see that the K is equal to 1.2 times 10 to the minus 3 molar seconds divided by my F2 concentration, which is 0.1 molar, and my ClO2, which is 0.01 molar. Now, when I do that division there, 1.2 to the minus 3 divided by 0.1 divided by 0.01 gives me a number of, for K, of 1.2. Now let's talk about units, and units are really important in kinetics because it does tell you sort of what is going on. If we look at this, the molarity up on top will cancel with one of the molarities on the bottom, and that will leave you 1 over molar seconds, or you could write 1.2 molarity to the minus 1 seconds to the minus 1. And that would be our answer for the value of the rate constant. Now, if you put into that formula right here the information for experiment number 2, you should also hit 1.2. If you put the information for experiment 3 in there, you should also hit 1.2. Because it's a rate constant, as we talked about, that is really the constant relationship that we have that will always end up being the exact same number. As long as you don't change the temperature or anything like that, to keep the same temperature. You could run multiple experiments starting with different amounts. you will always end up with the same rate constant because it's constant number again, as long as you don't kind of change the temperature. Now, first off, any questions on that calculation there? Now, earlier I talked about units and how important units are sort of with the rate constant. And for example, when we see these units of 1/molar seconds, those are the typical units for the rate constant for a second order reaction. So it does really make sense in this particular case that those units are correct. If you perhaps remember, I think yesterday we saw one where the rate constant was 1/seconds, and that's for first order. So the actual units of the rate constant oftentimes will tell us what type of order a reaction is. We're going to talk about those different orders of reactions in just a second here. But it's a good piece of information to remember. Any questions on any of those sort of steps? So a couple of things about rate laws and some of these things that we just talked about. Again, rate laws are always determined experimentally. So as we just saw there, you will be given pretty much a table, some type of table like that. Again, it may have 3 trials, may have 4 trials, may have 5 trials, may have a whole bunch of trials in there. Also, for the most part, probably 2 reactants is what you'll see. Sometimes you'll see 3 reactants, but in most cases, we usually don't have a lot of reactions that have 3, 4, 5 different reactions happening at once. So a vast majority of reactions that we actually see, are like 1 reactant through a decomposition reaction, maybe a couple of reactants in a double displacement, single replacement type reaction. So, we don't see a lot of reactions that have like multiple reactants, 3, 4, 5, 6 reactants. And that's why when we talk about certain orders in just a second or down the road here, we don't deal with a lot of big orders, first order, 0 order, second order reactions are very typical of that because of just how much reactants we typically have starting to react with one another. But they're always determined experimentally, these rate laws. The reaction order is always about reactants. So when we write rate laws, no products involved, just reactants. And as we saw there, the order is not the X and the Y's are not basically the coefficients. They could be the same number, but that's not, again, how you get it is from the balance equation. You do have to do that math and basically determine the orders like we just did there. Any questions on that there? All right, so why don't you take a second here and answer this question. The rate law is given there. Is the rate is 6.6 times 10 to the minus 5 when NO is 1 times 10 to the minus 6 and 3 times 10 to the minus 6. What is the rate constant? So take a moment or two and calculate it. Okay, so let's look at this one. This one, they actually gave us the rate law. So obviously it was found kind of like what we just did there. So the rate law that they gave us was K times NO and O3. We're looking for the value of the rate constant. So kind of like what we just did there at the end, we're going to rearrange this, and that would be the rate is divided by NO and O3. Again, just dividing these guys to the other side. At that point, we pretty much have all those numbers given to us. So the rate would be here 6.6 times 10 to the minus 5 molar seconds divided by our NO concentration, which was 1.0 times 10 to the minus 6 and 3.0 times 10 to the minus 6 for our other guy there. And it looks like, again, we get 6.6 to the minus 5 divided by 1 to the minus 6 and divided by 3 to the minus 6. And it looks like we end up with a lot of zeros. Let's see, 2.2. 2.2 times 10 to the 7. Again, on units, molarity there cancels, leaves us really with 1/molar seconds. And again, that is very much the units that we associate with what is referred to as a second order reaction. And we know that by looking at our rate law here, with the order is 1 here, order is 1 here. So when we add that together, 1 plus 1 is second order. So again, unit wise, everything matches well what we see. Any questions on that calculation? Okay, so why don't you try one here? We're actually going to calculate everything from some tables information. So I think we got this one next. So what we want to do here is we want to calculate the or determine the rate law with the orders. We also want the value of the rate constant with units. All right, so give that a go, see what you come up with, and we'll talk about it again. Find two where they say the same, and then reverse it, find two where the other ones say the same, and the other guy stays, basically varies. Okay, let's take a look, see how we're doing on this. So again, like I said, this is a typical sort of table. We have multiple experiments. Sometimes they're called trials. In this case, we have three. Like I said, you could have a table that has 4, 5, 6, a whole bunch of different trials. But these are the constant kind of things that you see in these tables. Again, we see the concentration of our reactants. We see sort of the initial rates that were sort of determined. And again, by the way, you can determine initial rates by doing some graphical type of procedures when you do an experiment and take the slope of the line. And a lot of times you can figure out the rate of the reaction from that. So that's sort of how those numbers are sort of achieved. A lot of times is through making graphs of experimental information. And, you know, in certain cases, you could just take the slope of it, of the line, best fit line, and you'll kind of get the rate from it. Now, to sort of figure out the rate law here, we would start with perhaps just a generic rate law, where in this case, the rate would equal K. Again, just our reactants involved, so S2O8 2 minus. Again, I'm going to call that to the X, and I minus to the Y. So again, the goal of this table is to figure out really what X and Y are first, and that will allow us really to figure out everything else. So as we talked about before, we want to go to this table. We want to find a couple of entries again, where one of the reactants remains constant and the other one varies. And by the way, in a rare instance where you do have perhaps 3 reactants, in that situation, you would want to find 2 entries where 2 of the reactants remain constant and 1 varies. So the goal is really just to have 1 unknown, 1 thing being varied, everybody else sort of being constant along the way. Here again, if we look at sort of the experiments 1 and 2, we do see that this guy's concentration stays the same while this guy's varies. So that's a good place to start. So we'll start there with those 2. So looking at experiments 1 and 2, and again, we want to kind of take the larger rate on top. So in this case, it looks like experiment 1 has larger rate. So I'm going to put all of experiment 1's information up on top in that formula that we used previously, rate 1 over rate 2 is equal to K to the A to the X and B to the Y, K, A to the X, and B to the Y. So putting everything from experiment number 1 up on top, 2.2 times 10 to the minus 4 is equal to K times the concentration of my S2O8, which is 0.08 to the X, times my concentration of I minus, which is 0.034 to the Y. So that kind of looks like a 4. Make that Y there, maybe Y-ish. Now we're going to take everybody from experiment number 2 and put it on the bottom again. You just can't mix and match. You got to keep everybody, all the information numbers together. So 1.1 times 10 to the minus 4, our K, and our 0.08 to the X, and our 0.017 to the Y. Now we could do some math here, and I believe if we divide that out, that's going to give us a 2. Again, at this point, we do not know what the rate constant is, but it is a constant number, which means it should cancel. At this point, we don't know what X is, but we do know it's the same number up on top and on the bottom, which means that these guys will cancel out. And lastly here, 0.034 basically divided by 0.017. I want to say that also equals a 2 to the Y. Again, we could take the natural log of 2 on the left and divide it by the natural log of 2 on the right, and that will give you y is equal to 1. Any questions on that part of the calculation there? So obviously using that information, we've now been able to determine that the order with respect to I minus is 1. We now want to go back to our table. And since we kept S208 constant before, we want to vary it, but we do want to keep I minus constant again, so we don't have too many unknowns. So it looks like what will achieve that for us is experiment 2 and 3 in this case. It keeps I minus constant, but it does vary our S208. So we're going to do the same thing. And it's looking like experiment 3 has a larger rate. So we're going to put that there on the top. So that would give us it for experiments 2 and 3 here. Going with 3 up on top, 2.2 times 10 to the minus 4 equals our k and our 0.16 to the x, 0.017 to the y. Putting everything from experiment number 2 on the bottom, 1.1 times 10 to the minus 4 k, and that's 0.08 to the x and 0.017 to the y. Again, that's going to give us a 2. K's are going to cancel. These guys here will give us a 2 to the x. These guys will completely cancel. And in this case, we actually end up with x is equal to 1. Again, a reminder that I know a couple of these examples or so, we've hit a lot of 1s, but they won't always be 1. But in this particular example, looks like it is. That means that we really can write our completed rate law at this point. And we know that the rate is equal to k times S208 minus, really to the first power, you don't need to write it, times I minus, also to the first power. That means that the overall order of this reaction is 1 plus 1, which means it is second order. And now that we have solved for the orders for x and y, we now can use our completed rate law here to basically figure out the value of k. And as we talked about before, you could choose any of these entries to figure out what the value of k would be. And in this case, we would want to rearrange our rate law, which the k is equal to the rate divided by S208 minus. And again, here, I'm just going to choose entry number 1 here as information. That means we have 2.2 times 10 to the minus 4 molar seconds divided by 0.08 molar and 0.034 molar here. 0.034, that's very bad. 0.034, there you go. And if we do that there, we end up with 2.2 to the minus 4 divided by 0.08 and divided by 0.034. That gives us something in terms of our rate constant of 8.1 times 10 to the minus 2. Again, unit-wise, molarity up on top and a molarity on the bottom will cancel. 1 over molar seconds, which as we've previously seen are the proper units for a second order reaction. Any questions on any of those there? Okay. So again, you can see this is typical information and how we solve it. Just to note, let's just say, for example, we did get an order of second order for I minus, and let's just say that our rate would be k S208 minus. It obviously is not correct here based on this information, but let's say we got that. How that would change, and again, sort of how the calculation would change. And again, it's not always going to be 1 and 1 for everybody. You can't get things like 2. You can even get things like 0 order and stuff like that. But if we did, first off, it would change because the overall order here would then be 1 plus 2, which would be third order. And when we go to solve for k, it would be important that When you divide it, you do need to make sure you carry the squared down. So the squared would be carried down as well. So again, this is obviously not the answer you would get for this problem. What we got is the correct answer. But just to illustrate that, sometimes people ask, well, what happens if you do have, an order that's not one? You do obviously put it in there. It will affect obviously the overall order, and it will also affect the value of the rate constant because it needs to be kind of carried down as well. Any questions on that there? So again, just to be clear, this is obviously the right answers here for this particular problem. Okay, so why don't we try one more here just to make sure. Again, from this information here, let's find all those things, what the actual completed rate law is, what the orders are for everybody, and the value of the rate constant as well. Okay, let's take a look here and see. So we'll proceed the same way. We'll start with sort of the generic rate law there. The rate is equal to K. Again, we're just going to include our reactants. Give that guy an X. You can use any letters you want, really. We'll give that guy a Y. So looking at our table here, we actually have 4 different entries, and we're just going to approach it the same way. And just looking at 1 and 2, it looks like we're going to keep this guy constant with 1 and 2, and this guy will vary. So looking at experiments 1 and 2, I'm going to go with number 2 up on top since it has the larger rate. So that would be 32.3 times 10 to the minus 7, which is important to make sure you read these tables and their titles important. Otherwise, it's very common people kind of miss the times 10 to the minus 7. Won't make a big difference in terms of your orders, will make a big difference in terms of probably your value of your rate constant at the end. So you want to make sure, again, sometimes in tables, people abbreviate or do some things like this. So you want to make sure that you do get the correct number there. This would be K, and again, our 0.06 to the X and our 0.2 there to the Y. And again, that is all the information from experiment number 2. Up there on top, we're going to put all the information now for experiment number 1 on the bottom. 10.8 also times 10 to the minus 7 would be K, or 0.02 to the X, 0.2 to the Y. Now doing a little bit of math here, we end up with 32.3 times 10 to the minus 7 divided by 10.8 to the minus 7, and that gives us a basically 2.999, basically like a 3, pretty close there on the round. It probably is okay here to round. Again, sometimes, especially with experimental information, you might not get really perfect numbers, but in this case, 2.99, pretty close to 3, good enough to round. These guys, again, will cancel as they're the same number. These guys here will basically give us 3 to the X, and these guys will completely cancel out to 1, basically. And that tells us that in this case, X is going to equal 1 in this case. Again, you can natural log both sides and divide. If you don't have perfect number, even if you kept the 2.99 here, if you kept the 2.99 is equal to 3 to the X, you could natural log the 2.99, basically gives you like 1.095 when you take the natural log of it. You can natural log on this side of the 3, natural log of the 3 gives you basically 1.0986, and the X comes down. When you divide those guys out, 1.095 divided by 1.0986, again, it gives you basically 0.997, which is pretty close to 1. So again, you can natural log it both sides if you don't have really whole numbers, maybe on both sides, and divide it. And again, pretty safe. You'll probably end up near a whole number or something like that. You at that point can round very close to it. Any questions on that there? All right, so if we did that, we now want to really vary the NO2 minus, but we do want to keep the NH4 plus constant. And just looking down the NH4 plus aisle here, it looks like it is going to be experiment 3 of 4 that's going to keep that one constant. And that obviously is varying our NO2 minus. It's using our same approach here. We see number 4 is the larger number, so we'll probably go with that up on top. That means, again, 21.6 times 10 to the minus 7 is equal to k times 0.2 to the x, 0.0404 to the y, dividing it out on the other side there by our number 3 on the bottom, 10.8 times 10 to the minus 7, our k, and 0.2 to the x, 0.0202 to the y. Again, here dividing 21.6 there divided by 10.8, going to give us a 2. Again, the k's will cancel. We know this guy will completely cancel, and that's going to give us 2 to the y. So again, y is equal to 1. And again, a very good reminder, maybe these aren't the best examples there since they all came out the same, but they will not necessarily always come out to ones. That means in this case, the rate law or completed rate law will be K, and that will be NH4 plus to the first. We don't need to put it there. And our NO2 minus also to the first power. That means that the overall order, much like the other ones, would be 1 plus 1, which equals second order. At this point, we can solve for K. So K in this case would be the rate divided by our NH4 plus and our NO2 minus. And again, we could choose really anybody from the table there to put our numbers in. Again, I'm just going to choose the first entry, but again, you can choose 2, 3, or 4 and put the numbers in. As all should come out the same. 10.8 times 10 to the minus 7 molar seconds divided by 0.02 molar and 0.2 molar. That ends up getting us 10.8 to the minus 7 divided by 0.02 divided by 0.2, and looking like we are ending up with a 2.7 times 10 to the minus 4, 1 over molar seconds, which again is what we're left with when one of these cancels. And that would be the value of our rate constant. Again, sort of the larger the value of the rate constant, the faster the reaction is taking place, the slower or the lower the value of the rate constant, kind of the slower the reaction is taking place. Any questions on any parts of those calculations? I'm not sure I understand your question about overlapping the experiments. So if you're asking when you go to the table, how you choose it, the goal is to, again, keep one of the reactants constant while you vary the other one. And that's sort of what you would do when you want to go to these tables. And then once you kind of keep one constant, you want to go back and kind of do the other one. Yeah, so it doesn't matter. So if your question is, like the previous one I did experiments, whatever it was, 1 and 3 or whatever it may be, and that type of thing. It really does vary depending on the problem and really the table. So there's no set formula of, which ones you should choose from the table always, because it is an experimental sort of table. So you'll have different values in each of these things. But really what you're looking for is what we did here. For example, on the first one, we're looking to keep one of these guys constant while the other one varies. And then once you kind of do that calculation, you then want to go back and basically switch it around and go, okay, I kept this guy constant. I then want to keep this guy constant. And again, this one varies. And that's really what you're looking for in terms of, how you pick out the experiments from the sort of data table that you would be given. And it is because, where's that formula there? We were just looking at there. That's right here. So when we talk about kind of rate 1 and rate 2, as I mentioned earlier, it doesn't necessarily mean that it's always going to be the first and second sort of entry in the table. It just means you basically need to go to a table and find, again, 2 entries where basically one of the reactants remains constant and the other one varies, and then kind of reverse it, and then find 2 other entries where the first guy that you kind of varied now stays constant, and the other one that you had constant varies, so that you could get those answers. Other questions on that? Now, earlier I was talking about, it's important to make sure, you look at the table and you don't miss something like this. You may be asking, well, I missed it, but I still got the same orders. And the reason you got the same orders is because of this math. When you're dividing here, these cancel. So it's basically just dividing these 2 numbers. Where it will make a difference is here. You probably didn't get the right answer here because you didn't have it here. So really important, you would have got lucky on this case in terms of the orders, because mathematically these guys would cancel out anyways, but you would definitely be off on your rate constant. So again, really important, especially with tables, as you look at the headings to make sure you're not missing anything. And like I said earlier in the last example there, although we've hit all sort of ones on everything, those orders could be 1, 2, 3, whatever it may be. It also could be 0. Just a reminder that when you have a number to the 0 power, that basically equals 1, right? So that's also sometimes a order that you come across is actually 0 order. And that would be something where if you got say like 4 to the x is equal to 1, basically x would equal 0, basically. So it is possible that you could obviously get an order of 0, and again that does equal 1. And you could do it the same way. You could take the natural log of 1, which is 0, basically divided by the natural log of 4, which would give you 0 as well. So I would say common orders that you see for x's and y's are 1s, 0s, 2s, occasionally 3s, but you don't usually see really large numbers like 6s, 7s, 8s, 9s, 10s, anything like that. And again, because they're really related to sort of how a reaction takes place, and if you look at the reactions here, and a lot of reactions that we see, we see a couple of reactants, maybe 1 reactant, maybe 3 reactants, but you don't see a lot of reactions where there's 4 or 5 or 6 type of things reacting all at once. And that's why we usually kind of see those orders for X or Y, or even the overall order as being 0, 1, 2, maybe 3 or so. And those are usually kind of common ones where kind of these guys are really the more common ones that we see a lot. Any questions on that there? Okay, now we're going to talk about we talked about these kind of overall orders. We're going to talk about specific orders of reactions. And the first one we're going to talk about is first order reaction. And we're going to talk about some of the important things for a first order reaction. So a first order reaction can be achieved by really 2 ways. You could have 1 reactant where the order is 1. And that gives you a rate law here of the rate is equal to K times A to the 1, which means the overall order here obviously would be first order. You could also have 2 reactants where, say, maybe A is first order, maybe B is 0 order, right? And that basically would be first order overall. So there's kind of multiple ways you get to a first order sort of reaction. A lot of times it does involve 1 reactant, but could involve 2 reactants where one of the other reactants are 0 order. And if we rearrange the rate law here and we solve for K, which is what they did here, and we just put the units in, the molarities here will cancel. And that gives us the typical units that we associate with a first order reaction. So why is that important, sort of understanding the units of the rate constant? Well, just a practical answer is in a lot of problems and kinetics problems, they will not necessarily tell you in flashing lights, this is first order, this is a first order reaction. But instead, what they'll give you is the value of the rate constant with its units. And when you see it and go, hey, that is a rate constant that has units of 1/seconds, that tells me that this reaction is first order. Why is that important? Because if the reaction is first order and you're trying to determine, how a concentration is changing with time, there is a specific first order reaction or equation that you use to do that, which is different than, say, a zero order equation, which is different than, say, the equation you would use if it was a second order reaction. So knowing the value there of the rate constant in terms of the units and what it means is really important. Now, we see units of 1/seconds, and seconds is a very common unit sort of used here in these reactions, but it doesn't necessarily always have to be seconds for it to be first order. It has to be some type of unit of time. So it could be 1/minutes, 1/hours, 1/weeks, 1/days, 1/years, but 1 a unit of time indicates a first order reaction. Why do we oftentimes say it's seconds? Because if you think about, say, physically doing an experiment, you probably are not going to be there for days, years, and weeks doing an experiment, the same run of an experiment. A lot of times we measure things in like seconds, maybe, right? A few minutes, which we can convert to seconds and stuff like that. So seconds is a very common sort of unit of time measurement that is done in experiments. Now, when we graph the concentration over time, we do expect concentration of A to be decreasing with time. And when we do that, we get this graph here on the left-hand side, which is the concentration of A versus T. We see as time goes by, our concentration of A starts to decrease with time. We could go through here basically and take the natural log and integrate this, and we get what is sometimes referred to as the integrated rate law, which is this guy right here. And this basically is kind of our time and temperature dependence, if you will, equation. Time and concentration, not temperature, sorry. Time and concentration dependence equation. And what this allows you to do is figure out certain things. The natural log of A here, this is our kind of final concentration. The natural log of A naught with the little circle on it is our initial concentration. That is our rate constant. And T here is actually time, not temperature. So it's actually time here. And this is the equation that you use specifically for a first order reaction. And if you know what your initial concentration was, you know how long you ran it for, you know your rate constant, you can figure out how much would be left over. If you know how much was left over, you can figure out how much you started with. You can figure out how long it would take for a concentration to get to some point. You use this to find out a lot of stuff and information. In addition, there is a half-life equation that is specific for first order, which is the natural log of 2 divided by K. You'll sometimes see 0.693 K. 0.693 is what you get when you take the natural log of 2 on your calculator. You get 0.693. And the half-life is the time it takes for half of whatever you started with to go away. So if you started with 10, after the first half-life, you're left with 5, right? And so forth. If we take this integrated rate law and we rearrange it as such, the natural log of A is equal to minus KT plus the natural log of A naught. That is that equation written in the form of a straight line, like y is equal to mx plus b. And in kinetics, we make a lot of graphs. And although this is a graph that is first order, the one that we usually think of when we're talking about first order reactions is the graph on the right, which is the linear relationship. That is because y means on the y-axis, I graph the natural log of A, which is what we have here. On the x, I graph t, which is what we have here. And if I do that, that should yield me a straight line, which as you can see here, a nice fit straight line, where the slope of that line will equal minus k, not positive k, but minus k. That's because this line's slope is negative. So the negative and negative will give me a positive value for the rate constant, which is what you should have. So when we talk about first order reactions, there's several things that are really important to remember for it. First off, the units of K being 1 over seconds, or again, 1 over time. This is the integrated rate law for specific first order reactions. This is the one you should use along with the half-life equation. And like I said before, this guy over here is typically the linear relationship or linear graph is the one that we associate with it. So those things are really important for a first order reaction in order to sort of calculate what you need. Any questions on that? Here again is a first order plot. We see the natural log of our reactant versus time, again, yielding our linear relationship where the slope of this line would equal minus the rate constant. And that's one way in kinetics experiments that you can sometimes graphically determine the value of the rate constant by making that graph. So why don't you take a second here and see what you come up with. This reaction is first order with a rate constant of 2.8 times 10 to the minus 2. How long will it take for A to go from 0.88 to 0.14 molar? So take a second, see what you come up with. Look here. So first off, it tells us it is first order. If it did not tell us it was first order, we do have the value of the rate constant given to us, which is 2.8 times 10 to the minus 2 reciprocal seconds. And it is those units of reciprocal seconds that would tell us it is first order. So again, not always will they tell you in problems, hey, this is first order, but they will give you something like this, the rate constant value. And when you see those units, that should indicate that it's first order. That should indicate that we do have some time and concentration. So we want to use the integrated rate law specific for first order, which is this guy. Now we have K. The 80 degrees is really useless information here. We're not going to use it in a particular calculation here at this point. Concentration of A decreases from 0.88, which would be our initial concentration. That's what the little knot means on the bottom there, to our final concentration of 0.14 molar. So we pretty much have this, and we have this. We are going to be solving for time. So if we put in our numbers, natural log of our final, which is 0.14, is equal to the natural log of our initial, which is 0.88, minus our rate constant, 2.8 times 10 to the minus 2 reciprocal seconds, and our time. I personally, when I do this, is I take the natural log of 0.14 or hit equals. Then I subtract this to the other side, the natural log of 0.88. And if you do that, natural log of 0.14 hit equals, then subtract the natural log of 0.88 to bring it to the other side, gives you a negative 1.838279, not rounding too much. Why not? Let's add a few more numbers. There we go. Equals minus 2.8 times 10 to the minus 2 reciprocal seconds, nRT. We obviously are then going to divide this to the other side, not only dividing the number, but there is a negative there that needs to be divided to a negative here. That way we do not end up with a negative time, which, as you know, probably does not occur, negative time. And that will get us something in the ballpark here of T is equal to, we'll call it 66 seconds in this particular case. The units are seconds from here. So when we divide it This is 1/2 So when we divide it, the seconds flip to the top. And we do end up with a time of about 66 seconds. So just about a minute it will take for this reaction to go from 0.88 molar to 0.14 molar. Any questions on that calculation there? Okay. Now, when you are using sort of this first order equation, or really any of these integrated rate laws where they have this part of it, you do want to watch the units of time. Sometimes they are different. So sometimes you may have reciprocal seconds here, but maybe you have days here on the right, or vice versa, or something like that. So sometimes the units of time can be a little problematic, as they're not the same. We sort of jumped a little bit ahead here and talked about the half-life for our first order reaction. But basically, if we substitute into that integrated rate law, the final is the initial divided by 2, which is the half-life. That is where we get our half-life equation. And again, this half-life equation here, which is the natural log of 2 over k. And again, if you hit the natural log of 2 on your calculator, that's the number you get. Is specific for first order reactions. So if we wanted to know what is the half-life of this as it decomposes with a rate constant of 5.7 times 10 to the minus 4, we would use our half-life equation, which would be the natural log of 2 divided by k. Putting that in there, natural log of 2 divided by 5.7 times 10 to the minus 4 reciprocal seconds. That gets us the natural log of 2 divided by 5.7 to the minus 4. Gets you about 1,216 seconds. There's 2 sig figs here, so probably about 1,200 seconds on some significant figure rounding in this particular case. And obviously that is about 20 minutes basically for this to occur. Question on that half-life there. Now, how did I know I should use the half-life equation specific for our first order, other than the fact that we haven't talked about any others? But again, here, if we go back to our rate constant, the units that we see associated with the rate constant, which is 1/seconds, tells us it's first order, tells us if we're looking for the half-life, this is the correct half-life equation to use. Question on that there. Oops. Again, obviously the units here. Okay. Question on sort of first order there. Questions on any of those things there that we talked about today. All right, we will lay it up there.